Okay, so I'm going to talk today about something that's near and dear to my heart, programming style, which seems unrelated to distributed computing. So we're going to talk about style today, and we're going to see how it relates to distributed computing. Okay. So a lot of computer science treats the program as a black box. Okay. It talks of the input and how that input gets mapped to output. So if there are two programs that, for the same input, produce the same output, then we consider the two programs equivalent. Okay, so if you've studied computing theory, you've seen that if those programs happen to be Turing machines, then it's impossible to create a program that tells if two programs are equivalent or not. But if what you're comparing are written in a less powerful language, the finite state automata, for instance, you can indeed prove whether the input-output behavior is the same or not. Okay. When you talk of programming style, considering the program as a black box, you're looking inside and seeing how it's coded. Okay, and in particular, and you can look at the source code for various reasons. And one good reason, from a pedagogical point of view, and from even a practical point of view, is trying to find patterns in this code. Okay, and what are patterns? It's some application-independent description of some component of the program. So if you've done 401, you've studied design patterns, and coding patterns are generalization of design patterns. In fact, we don't have to wait till Comp 401 to talk about patterns. I've taught Comp 110, which is a CS1 course, and we talk about patterns in 110. So when we look at loops, we first talk about counter control loops, where the number of times the loop will execute is known before the loop executes, okay, determined by some counter. And then we look at event control loops, where when the loop terminates depends on some event that occurs while the loop is executing. Okay. And we also look at the difference between use of recursion as an alternative to loops. Okay. So same input-output behavior, different ways of coding the program. Okay. So what are design patterns? They're patterns. They're also regularized ways of coding the application. And we wait till 401 to talk about design patterns, because they have to do with classes. Okay? So a design pattern is a way of decomposing some functionality, implementation of some functionality into a bunch of classes. Okay? And I've got three important patterns right here listed. And the observer pattern, let's start with that. That's a way of decompose. That says that there are two kinds of components in the application: observables and observers. And when the state of an observable changes, it announces the change to registered observers. So it sends notifications to observers, which can then go and query the observable for more information than what was sent in the notification. Okay. So that's a pattern that you can see in many different applications. Here's a more elaborate, more complex pattern. It divides the application with three classes of components, and this pattern extends the observer-observable pattern. So it has to do with interactive applications. That means there is some input and there's some output, and there's some computation that maps input to output. And input is processed by components called controllers. Okay. And they go and call methods in the model informing it of the information in the input. Model changes the state and now behaves like an observable, and it announces its state change to all of the observables. And some of the observables can be views, and a view is an observable. Some of these observers can be views, and a view is an observer that goes and displays output. Okay, so controllers handle input, models handle logic, and views handle output. And as before, the views can query the model for more information because they're observers. Now, this is the Smalltalk MVC. This is the original MVC. Okay, the web-based folks have got a different but related definition of MVC that we will not consider here. Okay. And anytime you decompose an application into components, you have the benefit that one component can change without changing the other component. Okay, so you get reusability that way. So controllers' views can have different implementations not known to models, or observers. They don't have to. A model doesn't have to know exactly how a controller behaves or how a view behaves. It just needs to know, for instance, that a view will receive its notification and do something with it. Who knows what it will do with it? Okay. And controller is just some object that handles some kind of input. Doesn't have to care about how the input is provided, whether it's provided through a GUI or whether it's provided through an audio input or through a good old console input, a TTY-like input stream. Okay, it's independent of that. So we understand somewhat through examples and through an abstract description of what patterns are. So what does this have to do with distributed computing? Okay. And to answer that question and why we are looking at patterns in distributed computing, we need to sort of ask the question, why does style matter? Okay. And we kind of already saw that it allows ease of change. But there's lots of reasons. Okay. Performance is one reason. So many people will argue that a recursive solution is slower than an iterative solution. Okay. And sometimes there are trade-offs involved. You can either have efficient be space efficient or time efficient. Okay. And that with the same input-output behavior, you can have different ways of coding the application. Lots of people will argue that actually, performance is not something you need to argue about. Either something performs better or not. Okay? Where the argument comes around is when it's not worst case times, when it is average times. For certain classes of applications, certain applications may give better average time, and for other classes, other ways of coding it may give time. Okay? But if you're talking about big O, then there's no debate there. Ease of coding, there can be some debate. Okay? So I'd like to believe that a recursive solution is much easier to code than an iterative solution, but you may disagree with me. And we're talking of ease of getting something right. Okay, so it's not that you just got something and that seems right; it should be correct also. And ease of coding is related to code understanding. So somebody else, when they look at your code, depending on the patterns you've used, it may be more understandable or less understandable. Okay. So if you use some well-known patterns, and if the reader knows those patterns, then you can expect that person to understand the code better. Okay. Again, there's some subjectivity involved here. Okay. Code reuse and extensibility, which is what we touched on earlier, that when you divide code into multiple components, then one component can change without changing the other component. So you don't have to rewrite the whole application if you want some changes to it. Just rewrite the components that changed. Okay. So these are 4 benefits that I could fit in one slide. And these are general benefits when you write any code. Okay? Distributed code is code, so you would argue that these benefits also apply to distributed computing. And I would argue that they apply even more strongly to distributed computing. Okay? Performance, a lot of distributed computing is about performance. Either you take some existing application, you want to make it higher performing, so you go and make it execute concurrently on different computers. Sometimes you just provide distributed access to a resource, in which case the networking time is an issue, and time required to make things consistent is an issue, and you'd like to keep that time as low as possible. So performance is certainly a big issue here. Ease of correct coding. So we saw last time that we can always use the networking abstractions to build distributed applications. The whole point of talking of distributed computing is to add a layer above networking, which means we're providing higher level abstraction, and higher level abstractions are provided to ease code. Okay? So ease of coding is a fundamental principle, fundamental goal of distributed computing. You will also see in this class, and you heard from people who've taken this class earlier, that it's difficult, not because you write a lot of code, but because that code is hard to debug, especially if you get it wrong. So it'll be nice if you don't get it wrong in the first place, and it'll be nice if it's understandable enough that when you get it wrong, you can debug it. Okay. So code understanding and ease of coding is important. Code reuse and extensibility. Often you take a standalone system which is not distributed and you provide distributed access to its functionality. So you take something that wasn't that meant to do distribution, to implement some functionality and add some features to it. So extensibility becomes very important. Okay? And how you add can vary, and so what you add can change. So when you first make it distributed, you have to change some existing code, and then when you modify the distributed functionality, you have to make some more changes. Okay? So evolution becomes a big deal, and good style makes evolution easier. Okay? But that's subjective. Okay? And this is not all theory for you. It's not something you have to memorize and reproduce in exams. You will see this in your assignments. Okay, so you will actually have 2 sets of assignments, and in each set you'll be taking what you've done earlier and extending it. Okay. And one of them will be the Halloween simulation I talked about last time, and the other will be a map reduce algorithm. Okay. So let's talk of the Halloween simulation and see how patterns are relevant to it, relevant to making it easy to code. So remember, the goal is that to take some functionality, some state. So here we have 3 processes. Each process maintains some state, which is replicated. So whenever one process makes a change to it, the state change is supposed to go to all other processes. Okay. So if the user left process, which is simulating a particular user, goes and says move 100 minus 100, the avatar moves in all simulations. Okay. So that's the goal here, and how would patterns help here? As it turns out, like I said, the standalone applications were written in 401, used the observer pattern. Okay. That meant that the command processor had a setter, set input string, which is a string which is the setter gets called when the user enters a string, and it first does some checking to make sure whether the input should be allowed or not. Okay, we won't get into that. What the reasons are for not allowing some input right now. But if the input is to be allowed, it goes and creates an event to describe the change. Okay, so in this case, the input string is being changed, so it creates an event in which it says the property being changed as input string. It goes and tells the observers what the old value of that property was, so the old input string, and it also goes and tells the observers about the new input string. By the way, the new input string is a variable that I need to correct here. I modified the code that it really existed, so this should be new val rather than new input string there. I'll try to correct it before I publish the slides. So basically, it takes the old value and new value and the name of the property and announces it. Okay, and it announces it to whom? To observers that are registered with it. And how do observers register with it? Well, they call a method, a registration method, which is in this case is add property change listener. Now, whether these methods are called add property change listener or add observer, what the kind of event is that is sent, that is not something that is decreed in the pattern. Okay, the pattern just says there should be some notification sent, some registry method provided, and the rest are implementation details. Okay, so that's how the command processor was written, and how does this help in the writing of the distributed component of it? Well, what we can do is create an outcoupler, a coupler that takes events, that's an observer of the observable, and whatever events it gets, it goes and sends it out to other processes. Okay, so the original model doesn't have to change, the view doesn't have to change, the controller doesn't have to change, nothing changes. We just add a new component that registers itself, and then when it gets the event in this property change method, it goes and somehow sends the event to remote simulations. Okay? And in your projects, you will see different ways of sending events. Okay? So what have we done? We took a standalone observable, which had some observers, okay? And we added a new observer, which I'm calling an outcoupler or event distributor, and which just distributes events to remote objects, and nothing else changed. Okay, so all these theoretical reasons I was giving you for componentizing an application, you see at work here. Okay, so observable and existing observer do not change, and new observer added for distributing functionality. It'll be nice if all our distributed applications involved just adding components and we didn't have to go and replace components. Okay, for this class of applications, this pattern works. There's another important class of applications where you do have to make some changes, and they have to do with high performance computing. Okay, so here the goal is that you take some existing functionality. We don't go and change the functionality. So here in this application, Halloween simulation, we change the functionality. Something that was standalone suddenly becomes a distributed, replicated application. Okay, so it's got more features. Okay, we can take some algorithm that we can do on a single computer with a single thread and go and change it so that its performance improves without changing the input-output behavior. Okay, so you might have, again, an interactive application with controllers and views and models. And your model initially could be standalone and single-threaded. And you say, oh, this becomes such a popular model, I'd like to go and improve its performance. So you want to make it multi-threaded. As long as the new model and the previous model implement the same interface, you have to change nothing else, but you do have to change the model. Okay? And later you might say, oh, let's go and distribute the functionality too. So you change it to a distributed model, and again, the rest of the components remain constant. Okay? So existing controllers, views, and observers do not change. But what we do have to change is the model and the code connecting into views and controllers. Okay, so let's look at the connection part. So what do we have? We have, let's say, a serial model first, and we have some views, two kinds of views and two kinds of controllers. Okay, and we have, and for this to work, we had needed to have connected the controllers, models, and views together. Okay, so the first two lines tell you that connect the controller, each of the two controllers to the model. Okay, so we assume there's a set model method. Again, this is implementation specific. There has to be some way of connecting. It doesn't matter how exactly you connect. And you say controller 1.set model serial model, controller 2.set model serial model, and then we have to go and add the views as observers to the model. So you say serial model add observer view 1 and add observer view 2. Okay. Now when you go to the concurrent model, okay, some things remain constant, the controllers and the views remain constant, the model change, and the connecting code has to change. Okay, I have to go and now say concurrent model dot set model, concurrent controller dot set model, concurrent model rather than serial model, and similarly you have to say concurrent model dot add observer rather than serial model dot add observer. Okay. So a question point is, and for distributed model again you have to change the connecting code and change from a concurrent to distributed model. So a question at this point is, and like I said before, serial model, concurrent model, and distributed model must implement the same interface. So interfaces become important. Okay, another stylistic point. Okay. So one question at this point is, could we have somehow used some pattern that did not require us to make all these changes to the connecting code? Could the connecting code also have remained constant? Which seems impossible. I mean, after all, the model has changed, so you should go and have changed something. But maybe we want to reduce the scope of the change to maybe only one line rather than 4 lines here. Okay, so how can we reduce changes to the connecting code? Okay, what kind of pattern have you studied in 401 that would allow you to do this? And somebody's raising their hand, but I'm not going to take the answer because I'm glad you thought of the answer. And I named 3 patterns earlier. We've talked about 2 patterns, observer and MVC, so the answer must be the 3rd pattern. okay, which is the factory pattern. I don't know why it was trying to shut down on its own. Um, so factory pattern. What can we do? Here we've not used factory. Okay, so and that's why we had to make all these changes. And because we haven't used the factory, we're doing things directly. We're directly going and finding what the model is and connecting it to the controller and connecting it to the view. The factory pattern provides a level of indirection. Okay, so you don't directly find the model. You do something like this. Okay, there's a model factory that from which you fetch the model. Okay, so you go and say controller dot set model, model factory dot get model, and controller 2 dot set model, model factory. And again, when you're connecting the views to the model, we don't use the model, refer to the model directly. We say model factory dot get model. Okay. Somehow the right model must have been stored in model factory, or has to be retrieved from model factory, and we'll assume that the model factory also has a setter method, and in that setter method you change once with the model you want. Okay, so that part is model specific, but the rest of the code is not model specific. Okay, so now when you're to concurrent model, you change the concurrent model and you change the factory. You call a method in the factory. Okay, so you reduce the amount of change you have to make, and arguably that's easier to code, easier to change. Okay, I say arguably because ultimately you need to do some programmer studies and go and see what the programmers felt, how much time they took. Okay, but you can sort of argue that this is going to be quicker. Similarly for distributed model. So connection code is used, and what's a factory? Factory is a level of indirection which requires you to, when you use a factory pattern for some class C, so given a class C whose instances you need, you define either a factory class or a factory object associated with that class C. You don't instantiate only the factory class is allowed to instantiate that class, and anybody else who needs to go and get a value of that class, instance of that class, goes and says calls a get method in the factory class or the factory instance, okay, which gives you an instance of that class C. And you also might have a setter method to set the returned object, which is what we did in the previous application. Okay, so anybody who invokes a setter method is allowed to instantiate the class, but hopefully that's only one piece of code. Okay, and it's used for two reasons. We talk about programming interfaces, and we talk about an interface being implemented in multiple ways, and that allows us to change the application. So how do you exactly reduce the work required to change the application? Well, you use a factory that chooses between these interfaces. Okay, so when you have multiple interfaces, when you have an interface being implemented in multiple ways, then a factory class allows you to go and get the desired implementation. It's also used for enforcing singletons, and that is where it's important to make sure that nobody else instantiates the object directly. Okay, what's a singleton? Singleton is a class that has only one instance. Okay, and how do you ensure that there's only one instance? You only allow the instance to be retrieved from the factory, and nobody else is allowed to instantiate the class directly. Okay, you can do that through Java rules or just through a convention. Okay. So we've seen the use of the three patterns for high performance computing problem. These are often also today called big data problems. And here's the classic or the canonical big data problem being used to illustrate the benefits of patterns. Okay, so if you look at high performance computing and distributed computing, MapReduce will be the first thing that will come, probably be the first thing you'll see. And if you look at MapReduce examples, the first example that will come up will be this token counting example. Okay, the idea is that you're given a list of tokens, list of strings, and that's the input, and the output is the number of times each string occurs in that sequence, each unique string. Okay, so here I've typed a line for with a bunch of tokens, and the orange token appears 3 times. So the answer says orange is 3, apple is 1, and so forth. Okay. So we can do this application without any patterns. That's what I've done here. The application asks for input and produces the output we want, and then it asks for some more input. I made it interactive, so to illustrate the model view controller pattern. So how would we use model view controller here? Oh, I thought I got rid of these. But anyway, this is something you have to do in A1, and you can, as you do various parts, you can run the checks that I have provided you, and if you did what I showed you there, you will get 10 points for at least getting the functionality right, but only 10 points. Okay, there's a lot more points, and they have to do with style. So here's how we can change the style to use model view controller. And remember, the controller does input. So now the prompt, and here I'm providing traces. Okay, I'm providing a trace of who's doing what, and also which thread is doing each task, because later we will make this application concurrent. So we have to know, how functionality gets mapped to threads. So now we know this. We know that there's only one thread here because it's single threaded for now. Okay, that's what happens in A1, and we are describing which component is doing each piece of work. Okay, so entering a prompt is part of controller. It has to do with input processing. So the controller is the one that prompts. It gets the input. Then it gives the input to the model. We don't quite see that step here. The model, it gets the input to the model by calling a setter method in it, a set input string method in it. The set input string method announces a change to all its observers. One of these observers is the view. So the view goes and says, oh, I got a new string, and that new string is the sequence beginning with orange, apple, and so forth. So it gives you the whole string as the new value of the new string property, of the input string property. Okay, so that is how the input was given to the model. The model has to now compute output, or has to now transform the input. So it magically converts the input into a map in which the key is the token and the value is how many times each token appears. Okay, and it announces that to the view also, and the view says, oh, I got another property change. The name of this property happens to be result. Okay, result is now not a string like my input string was. It's a map, and the value of the property is the map. And in the map, I've got orange equals 3, apple equals 1, and so forth. Okay, I've got the key value pairs. Okay, so that's the end of the result, and now the controller gets into the action and prompts the user for more input. Okay, same functionality. The input output not quite the same, just because we've massaged the input output with some trace information, but fundamentally they're the same. Okay. So we've used a model that was created for distributed and non-distributed applications, and we've used it for an application that will become distributed later. And now here I'm showing you the use of another pattern, which is the map-reduce pattern, which is meant for distributed computing. Okay, so the model view controller pattern prescribes how an application is decomposed, how an interactive application is decomposed. You may or may not decompose it. The map-reduce problem says how some computation is to be decomposed, okay, into components, so that it can be distributed easily. Okay, and there are two. So map-reduce stands for mapping and reducing. Okay. What does mapping do? Mapping takes a string and converts that into a key value pair. How that's done is up to the mapper. Okay, reducer takes a sequence of key value pairs and creates, in our example, a hash table with key and value, keys and values. Okay, so it takes a sequence of key value pairs. Okay, uh, and then converts that into a hash table with keys and values. Okay, and so that's what you're seeing here. You see that orange was first mapped into orange, comma 1 key value pair. Apple was mapped into another key value pair called apple, that is apple comma 1. And then a reducer worked with these key value pairs to create an ultimate, takes this sequence of key value pairs and then produces a hash table where the keys are the unique tokens in the string, and the values are the number of times the sequence appears. Okay, this will all make more sense when you actually do the assignment. Okay, the point here is that we've prescribed how the computation should go. We've said that there should be some mapping first and then some reduction later. Okay, so that, again, the use of a certain pattern. Okay, and why did we? I motivated model view controller, and you're probably wondering why I did the key value, the map reduce thing. That gets motivated by this example. I've changed the problem. Now the problem is to take a sequence of tokens as before, assume these tokens happen to be numbers, and add them up. Okay. Because we are doing map reduce, again we will go and first convert each input value into a key value pair, do the mapping, and then we do the reduction. As it turns out, the mapping will be different, but the reduction step will be identical. So to go from that application to this application, all we have to do is change the mapper object and nothing else changes. Okay. Again, this will make more sense when you actually implement the application. Okay, but for now, intuitively, just imagine that there are two steps here, and one step, as it turns out, which you'll see, the reason you'll see later, is common, and one step is different. So, to summarize, coding structures are important, particularly for distributed computing as opposed to non-distributed computing. And there's some things that are going to be highly relevant for our assignments. And three particular patterns that I've talked about, observer, MVC, and factories, are all going to be very relevant for the examples I show and also for the assignments you do. Okay. Those are not the only patterns we'll study. Okay. MapReduce provides more patterns. Okay. And some of these patterns we will go and actually study. And a subset of the ones we'll study, you'll actually implement in assignment 1. How these patterns work in general and the theory behind them, we'll talk about later. Okay, so we'll do other, as we talk more about concurrency and distribution, we'll study them in class, in lectures. For now, what I've said in this lecture and what is in the assignment are sufficient to do A1 and to get a basic use of MapReduce. Okay.